Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we talked about transistor and its various applications in device like transistor as switch, transistor as amplifier and transistor as device basically. So that was all we discussed in last class, and here in semiconductor and semiconductor devices there comes one more thing, and that is basically digital electronics. So here we talk a little bit about type of signal. There are two type of signal, digital and logical, like digital and analog signals. So and there also comes decimal number system and binary number system. Sometimes just these two things are asked, that's why I will be discussing them thing. And we will talk about logic gates and some operation, boolean operation. So this is a small topic, like sometimes in small exams like maybe JEE mains also, and other exams some questions are asked based on it. So let me just first talk about some number system. So there are two, basically decimal number system and another is binary system. So what is decimal number system? Decimal number system basically the number that we normally study in mathematics or that we use in general life, that is basically your decimal number system. So here in decimal number system there are 10 digits in decimal number system. Ten digits are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these numbers digits are used in decimal number system, and the base is 10 for decimal number system. So here it means basically if I am writing, let's say 2025, so this is your number in decimal system basically, and here we write this is LSD and this is MSD, sorry not T. So LSD means least significant digit, and this is MSD means most significant digit. So if I like break it down into the like their place values and significant value for that place, that digit, then it can be written as like 5 into 10 raised to power 0. This is base, so we will multiply base power, right? And then it's 2 multiplied by 10 raised to power 1 plus next digit 0 multiplied by 10 raised to power 2 and plus 2 multiplied by 10 raised to power 3. So 10 power 0, 10 power 1, 2, 3. Here it's like because base is 10, and then it will be like this is the most significant digit actually, that is 2, and 5 is least significant. So this will be equivalent to like how much? 2000 plus this is 0 plus 20 plus 5, and if we are adding it then also we are getting 2025. So in this manner, like this is normally that we study, this is your called decimal number system. There comes another that is called binary number system. So how it is different from decimal number system? In binary number system there are only 2 digits in the binary number system, and those digits are basically either 0 and 1. For logical operations 0 and 1 also referred. For 0 means like low, 1 means high, true, false, something like that. Actually there are many meanings in logical operations that we will use in logic gates also. So binary number systems used in logical circuits, logical devices and like that. So what is exactly? So here first thing is there are only 2 digits, and the base in case of binary number system is also 2, right? So here what is that? Like here whatever the number you will write in case of binary number system, everything, all number will be either in terms of like 0 and 1. There will be no other digit. Like I can write it's like 101. So what is this like? we do not understand it exactly. It's not 101. This is something else actually. Convert one. This is binary number system. We can convert that into decimal number system. So again, here also this will be what? Least significant digit. This is most significant digit. And the conversion, is it, of this number, there is process actually, like to convert this binary number into decimal, and similarly there is also another process to convert like decimal to binary, right? So first thing is what it mean actually, like this number we can write this is equal to like again 1 into 2 power 0 plus this is 0 into 2 power 1 plus this is 1 into 2 power 3 2, right, to convert it. So exactly by like, because here base in case of binary number system will be 2, so we will like here we were multiplying it by 10, is it power, now here we will be multiplying by 2 power, so because base is 2, so this is equivalent to basically what, 1, and this is 0, and this will be equal to what, 4, so it's equal to basically 5. So 5 in decimal is written, this is 5 in decimal number system, and if I write it into binary, then it will be written as 101, is it? So this is the method to convert actually decimal like binary to decimal. Similarly, how we can convert a decimal to binary, let me tell you that. So decimal to binary conversion. Here the point is that in normal system that we study 2025, that is your decimal number system. So here you understand very well what it actually mean, what is the number and multiplication, division, everything you know actually for this system. Here this system is binary number system, there only 2 digits are there, 0 and 1, and it's different actually. So like this is actually equal to 5. So 5 in decimal written this way, 5 in binary number system it's written this way. Here multiplication division operations are also like different actually. Here we normally do not do such operations actually, like here things are different, so we will see a little bit about them also. So this is simply a binary number system. Now how we can convert a decimal number system to binary number system? So let me first tell you this directly with one example, then you will understand it exactly. Its method is simple, but it's very simple, nothing complex. So conversion of decimal to binary. So let's say I am writing this is 62, or let's say 63, this is a decimal number or number in decimal number system. Now I want to convert this into binary, then what I will do, basically we divide this 63, we divide by 2, and the remainder we write here. So like if I divide 63 by 2, how many it will be, like 331 times, remainder will be 1, it will be written here. Next again I will divide by 2, then it will be 15, and here remainder will be 1. Again divide by 2, then it will be 7, and I am getting still 1 remainder. Next again divide by 2, then you will be getting 3 and remainder 1. We will keep on dividing until we are not getting finally here quotient 0, right? So then if I divide it 1 more time, then there will be division by 2 to 3 1 times, and remainder will be 1. Now if I divide here again, so you can see actually there will be no quotient, quotient will be 0, it will be divided 0 times, remainder will be still 1. Now here this is least significant digit and this is most significant digit actually. So 63 in case of decimal number system is equivalent to, I will here like fortunately, or you can write unfortunately, all like digits are coming out to be 1. So if I write in either sequence, it will not make much difference. But if some 0 is coming here, then if I am writing it 1 0 this side, it will be different meaning. If I am writing 1 0 then and this side, things will be different actually. So I will give you one more example so that you are clear with that part too. So let me write. So now here 63 in decimal is equivalent to, here this one will be written, the next one, and this is next one, and this next one, and this next one. So this is actually 63 in decimal, and this 111 in binary. Now see, let's convert this also into decimal. So for conversion we will use same process, this with base 2. So what I will write, this is equivalent to, see 1, so I will write 1 multiplied by 2 power 0. Next 1 multiplied by 2 power 1, 1 multiplied by 2 power 2, 1 multiplied by 2 power 3, 1 multiplied by 2 power 4, and plus 1 multiplied by 2 power 5. Because how many, there are 6 1. So power 0, 1, 2, 3, 4, 5, it will come up to 5. Now it will be what? 1. This will be 2, 4, 8, 16 and 32. Right? 32 plus 16, it's how much? 48. 48 plus 8, 56, plus 4, 60, plus 2, 62, plus 1, 63, and that's what exactly we are getting. So this is coming out to be 63. So I hope you are understanding this decimal and binary number system. There are two number system. Decimal number system you are very well familiar. Binary number system, it's a little bit different. Here all numbers are only expressed in 2 digits, either 0 and 1. So like this is a binary number system. Here base is 2. To convert a binary number to decimal, we will use, this is the process, right? And conversion of decimal to binary, what we do, decimal number is divided by 2. We will keep on dividing and we will write the quotient down and the remainder here. So we will keep on dividing by 2 until we are not getting the quotient here 0. When 0 is there, then we will stop. Is it? Always 0 will come finally. We will stop. And this is your remainder. So remainder will be written in a form such that this, whatever the digit coming here, will be your least significant digit, and the last one, remainder, is your most significant digits. So in that way we will get conversion of decimal to binary number system. And let me write one more example, it will make more sense. So let me convert 85. Again the process is, I will keep on dividing, will write the quotient here. The division process will continue successively up to the final situation when quotient is coming out to be 0. So here what will be? It will be 4, 2, and remainder will be, remainder I will be writing here. So remainder will be again 1. 42 multiplied by 2, 84, remainder will be 1. Next again 2. So it will be then how much? 21, remainder 0. Divided by 2 again, then it is basically 1, 0, remainder 1. Divided by 2, then it's 5, remainder 0. Divided by 2, then again it's how much? 2, remainder 1. Divided by 2, then it's 1, remainder 0. Divided by 2, now quotient will be 0 and it will be 1. Is it? So this is actually 1, 0. That is also like coming. So this is what? Least significant digit. This is most significant digit. So this 85 is equivalent to, this will be 1, then 0, this 1, then 0, this 1, then 0, and next 1. So here also fortunately the sequence is like there is no much difference. It's coming either way I'm writing, and still you will be getting exactly same expression. Let me give you one more example. So let's convert 67 to like the binary number system. So what I will do, divide by 2, remainder will be written here. So it is 3 and 3 and remainder 1. Again divided by 2, then it will be like how much? 16, remainder 1, divided by 2, 8, 0, 2, 4, 0, divided by 2, 2, 0, and divided by 2, 1, 0, divided by 2, 0, then it will be 1. So here you can see it's different actually. So this is again least significant digit and this is most significant digit. So now 867 will be equivalent to like 67 in decimal number system, and this will be written, now 1 will be written this, then 0 and this 0 and this 0 and this 0, then 1 1, so 1 1. So this is 67 in case of decimal number system, and that is equivalent to 1 1 0 0 0 0 1. This is 67 in binary number system. So first thing is, what is binary number system, what is decimal number system, that must be clear. It's different ways of dealing, ways of writing an expression, writing a number. In case of this, there are basically in decimal number system there are 10 digit, base is taken as 10. In case of binary number system there are 2 digit and base is also taken 10, 2. And the conversion process, how we convert a decimal to binary this way, decimal to binary this way exactly, and decimal to binary. Similarly, if this is binary, then conversion of binary to decimal also I gave one example, and let me write here this conversion. So conversion of binary to decimal, we will multiply by base actually. So next is binary to decimal. So we have already converted decimal, is it, to binary. Let's check it, and that will be also process of conversion of binary to decimal. So first thing is binary, it's 1 0 0 0 0 1 1, right? 4 0 and 2 1. So this is your number in binary. Let's check whether it's coming exactly same. So the conversion process, again, this is least significant digit and this is most significant digit, and it's, you can write, we start from 0, so this power 1 2 3 4 5 6, so there will be power 6, so we will write it's 1 multiplied by 2 power 0. For we will write like this number, basically digit, that is 1, then multiplied by base power 0 1 2 so on. So next for this one I will write 1 multiplied by 2 power 1, next 0 multiplied by 2 power 2, then 0 multiplied by 2 power 3 for this, because right, and similarly for this 0 multiplied by 2 power 4, then for this 0 multiplied by 2 power 5 and plus 0 that is last one is 1 multiplied by 2 power 6. So conversion of this is what, binary number. To convert it into decimal, this is the process. This digit multiplied by base 2 and power, that is the place 0 1 2 3 so on, actually up to last. So now then you will write it, this is equal to how much, 1, this is equal to 2, this is 0, here this is 0, this is 0, this is also 0, and plus 2 power 6 equal to how much, that is 64. So then 64 plus 2, 66 plus 1, that comes out to be 67. You can check, it's exactly same. So this is all about number system, binary number system and decimal number system, conversion binary to decimal and decimal to binary. So I hope you should be clear with this. So if anything comes asked about this system, you should be in position to answer. Conversion, either system, what is exactly that system. Let's next talk about signal, that is digital signal and analog signal. Then we will talk about gates, logic gates. Okay, next is analog circuit and digital circuits. So there are basically two type of circuit, analog and digital. Here in case of analog circuits, the current or voltage varies continuously, right? Like this way you can see this is one of the example of analog circuits. In a circuit, if current or voltage either one of them is varying continuously, then we will call this is a analog circuit. So these circuits are also used for transmitting signals. So many times signals are transmitted in the form of varying current and voltage. So they are like this type of signal is called analog signal. So such voltage and current signal are called analog signals. So this is one of the example of analog signal. And there another is digital circuits. In digital circuit, the current or voltage basically has only two values, that is one is 0 and other is constant value of current or voltage. So a circuit which is having only two value of current or voltage, one is 0 and another is some constant value of voltage and current, that circuit is termed as digital circuit. So in digital circuit you can see one of the possible case here, let's say V and this is T. So some high constant value, then 0 up to some time, then again high some constant value, then again 0 for some time, then again high some constant value. So this circuit is it where I voltage or current, it's not V versus I, it's either V or I here, which is varying with time, but it's taking only two values, one is 0, another is some positive or some constant value of voltage and current. So that's circuit we will call digital circuits. So similarly, if a signal is transmitted in this changing like voltage or current, we will call that as digital signal, is it? So another is so you can write a signal which has only two value, that is 0 and some constant value of current voltage is called digital signal. So these are two type of circuits, digital circuit and analog circuit. In case of analog circuits we use like where continuously current changing voltage and current is there linked. So if it is continuously changing, we will simply call it analog circuit, and the signal which is transferred or used in this form, we will be calling it analog signal. Another one is digital circuit. So here current or voltage take either some 0 value or some constant. So we basically write it 0, it's written as 0, and this constant value, constant some high value, so it may be let's say some 5 voltage, 10 voltage, 20 voltage, something like that. So we mark it high. So this is low and this is high. Only two values will be there. So we write it basically like if I am writing low by 0, then it will be by 1. Here 1 doesn't mean the voltage is 1. 1 means like this digital circuits we use basically binary system, number system. So for low we will write it 0, for high we will use it 1. So these such type of signals and circuits are used in our calculators and computers. Actually computers and calculator and all such digital like devices, they understand only binary number system and binary logic. So that's why we operate like different operations are done. Let's try to understand. So there are some devices basically which uses those semiconductor devices and create some logic which actually like interpret these digital signals and digital circuits. And let's try to understand some of those, and we call that logical circuits, or we call them logic gates. So gates are some proper like some devices basically designed for some particular operation on this binary number system, or you will write this digital signals. So we call them logic gates. Let's try to understand that part. Okay, a logic gate. So logic gates are basically digital circuits which work according to some logical relationship between input and output voltages or signal. Basically it either allows some signal or block it completely. The main function is sometime it will allow. Now the point is like when it will allow, when it will not allow. So based on that there are different possible combinations and different possible like logics can be made, and based on that we have many type of logic gates. So the main function of logic gates is to control the flow of information, and there are many type of logic gates. The primarily gates that we will discuss, so the primary, we can write the main types of logic gates that we will study here are, it has like NOT gate, another is OR gate, AND gate. These are name of these logic gates because based on their function, what exactly they are doing, what operation they are doing, based on that we have given them names. So names, then one is NOT gate, OR gate, AND gate. Similarly there are NOR gate, NAND gate, and exclusive OR and exclusive NOR. So these are few type of gates that we will discuss about. So these have like every gate has some like symbol. There are certain symbols. So each gate, logic gate, has a special symbol. So that this is denoted by that symbol, represented in circuit by represented by that symbol, special symbol. And the function, like what exactly is their function, we can understand that function, or we can write that function by truth table. So there is a truth table about for each logic gate. So what is truth table? Truth table basically it define the function of each logic gate and it gives all possible logic level combination for input and corresponding output. So truth table basically is used to define the function of each logic gate. For each logic gate there is proper symbol, I will write that, and to define like their function we have truth table. Truth tables basically gives the information about all the possible logic level combination for input and output. So that way we can understand logic gate, what exactly every gate does. And the thing is that to understand this in mathematical term, there is a proper mathematics for that, and that we call basically Boolean algebra. So Boolean algebra, this also sometimes help you in understanding and solving problems. So Boolean algebra, you can understand, it is the mathematics for solving logical operations or solving or understanding the logic gates. So that is defined as Boolean algebra. So we will talk a little bit about Boolean algebra, the rules, and like because things are here different, it's like binary system will be there. Digital circuits, whenever digital circuits are coming, that means always it's binary, means it understand either high or low, it allow or stop, it's that way. But only two possible ways are not there, that allowing and stop. There are many logical like operations can be performed. Based on that, we have different, like which operation is being performed. So we have different logical circuits or digital circuits, and we call those digital circuits basically gates. Is it? So these are some of the possible gates. Each gate has some particular like symbol to represent, to write them, and has special function. So those functions are represented in truth table. Basically, truth table tells the different possible combinations for input logic levels and output logic levels to understand their mathematics, basically for logical operations. For that, we have Boolean algebra. So we will talk a little bit about Boolean algebra, and let's first understand the function of each logical gate and how it is represented. These actually gates can be realized by the semiconductor devices that we studied in the last lecture or up to last lecture. By using those semiconductor devices, these logic gates can be realized, means can be formed actually, like how exactly, like we understanding, okay, allowing and not allowing, but that can be like in circuits or in digital circuit can be performed, can be like those can be realized by some semiconductor devices. So first let's talk about these different types of logical gates or logic gates. Okay, so first is NOT gate. What is that? So let's suppose in digital circuit we have only two inputs, means two variable, two values can be either high or low, means either 0 or 1. So some input is given and we want that input to be inverted. Is it? For we are giving inputs high and we want output to be low, and vice versa. If we are giving high like low input, we want it to be high. So that conversion or inversion of input can be done with the help of this gate, and that we call NOT gate. So NOT gate is basically, it's like negation. Its main function is negation or inversion of input signal. Input, you can write signal. So if you are providing means high input, then output will be like, output will be high input, this is input, then we will get output will be low, and vice versa. If we are giving low input, then output will be like high. So this function is performed by NOT gate. Symbol for like NOT gate is this. This is the symbol. Here we give input and here we get output Y. So let's say, and in NOT gate we give only one input actually, and that is like either high or low. So A only one input, and correspondingly we get one output. Symbol this. What will be the truth table for this? So truth table basically give you all the possible combination for like logical relations. Is it? So here it's A and this is input and Y is output. So input can be 0 means low, or it can be high. So what it does actually, like 0 it will make it high, means low it will make output high, and high then it will make output low. And this is like, because to understand it mathematically we have something like that is called Boolean algebra. So Boolean expression for NOT gate that we can write Boolean expression that Y is equal to A bar. Here A bar means basically or inversion, is it, or complement basically. So A inverted, that. So this is the Boolean expression for NOT gate. Okay, next is OR gate. Let me first tell you the function of OR gates. Let's just try to understand here. So here we have two switch are basically equivalent to your two inputs. So in case of OR gate we have two input A and B input variable, and we finally get one output variable Y. So it's equivalent to this system. So output is basically here, means this bulb, if it is either it will glow or it will not glow. So what will happen, battery is connected. If I am switching this on A and B is off, means A on means high, so it's like 1, and B means off means low. So 1 and low, then still bulb is glowing means high, we are getting output. When A is off and B is on, then also we are getting high, actually bulb is still glowing. If we are switching both these like switches A and B, still it will be like on. So in either case you are like one high and another low, or first low, another high, in or both are high, then in all cases we are getting high, and means bulb is glowing. And there is a one possibility when both are low, then we will get low output. So this is one particular type of operation function, and this can be done with the OR gate actually. So function of OR gate we write basically here the Boolean expression for OR gate, Boolean expression for OR gate. So y is given by a plus b, here written it's read as y output is equal to a or b, is it? And so this is Boolean expression. The realization of this gate can be done by using two diodes. So these are two diodes connected and one resistor here, and this is the output y. Now see here, so diode 1, diode 2. So when a is high, is it, or I will write a, let's say 0 and b 0, this means diode 1 not allowing, reverse bias not allowing, what we will be getting here output. So you can get y output will be 0. When a is high means I will write a equal to 1 and b is 0 means low. So a is high means it will allow current to flow and output you will get some high. B is 0, it will block, reverse biased, and so on. You can check all the possible combinations. So this is the way, with the help of simple two diodes we can realize a OR gate actually, and output we are getting. The truth table for this we can write. So truth table here, first thing is we will have two inputs, right, and one output. So y is output and these are two. And what are like possible number of number combinations for inputs? So possible number of combination for input, so that can be given by 2 raised to power n, where n is the number of variable. So how many variables are there? N is number of variable. So here we have only two input variables, right? N is, you can write number of input variable. So input variable a and b 2, so 2 raised to power 2 means 4 possible combinations will be there. So 4 possible, 0 0 1 1, then 0 1 0 1. So these are like one combination, two combination, third and fourth. So in this situation, like we can write here when both switches are off, then what we will get? 0, low. Either one of the switch is on, then we will get still high, and similarly high, and both are on, still we are getting high. So this is the truth table for OR gate. You should be understanding what exactly operation it is performing. In Boolean expression we write it's like y output is given by a plus b, right? So and this is the realization, and this way you can understand like high and low, when it will allow the current or voltage to pass and when it will not allow. So this is about OR gate. Next is AND gate. The symbol for AND gate, it's this way. It's different from OR gate. You should keep the remember the difference between this is actually OR gate and this is AND gate. So it's just little bit difference between and OR gate. You should not get confused between these two. So the symbol for AND gate is this. Its Boolean expression is written as A dot B, and this is written actually read as y equals to A and B. So we read this expression, Boolean expression, as A and B. Don't go for it actually. So here the logical operation of this AND gate is equivalent to this. So here what happened actually, one battery connected to bulb and two switches are connected in series this way. So now what will happen actually, either of the switch, let's say this is on, this is off. So means this again 4 possibilities will be there, 0 0 1 1 0 1 0 1. So in one possibility 0 0 means both switches are off. What will you will get here? Will your bulb glow? Definitely not. So you will get 0, right? Next case, 1 is high, B is 0. this is, or I can say A is 0, B is high. In this situation, this switch is on and this is still off. Will we get will bulb glow in this situation? Definitely not. So you will get still 0. Another case, this is high, means I'm switching it on, this is off, and in that situation also you will get 0. When both the switches are on, then you can see circuit will be complete and we will get high or bulb will glow. So this is the function of AND operation or AND gate. The realization of this AND gate can be done with the help of two diodes connected in reverse bias. So D1 and D2, and one battery connected here, and resistor, and Y is the output. Let me tell you how it actually like work, how it exactly realize the AND gate. So what is happening here? High voltage is there. Now when A and B both are 0, first operation A equal to 0 and B equal to 0 means these two are not connected to high, they are low. Then what will happen here? Potential will be like at this point potential will be high, and both the diodes will be like forward bias, D1 and D2 forward bias. So what will happen? Current will flow in this direction, and you can write here 0, and this is V and minus IR. So Y I can write potential V minus IR. Now you can see, because D1 D2 both are forward bias, here it's low, here it's high. Forward bias current will be going this way, high current will be there. So when current I is, you can write high, Y will be what? Low. We will get low output. So in this situation we are getting 0, A 0, B 0, we are getting Y output also 0, means low. Next situation, let's say one of this is connected to high. Then what will happen? This is connected to high, so this will be like, now in this situation here also voltage is there, but this is even higher, so this will be reverse bias, it will not allow the current to pass, but this is still low. So what will happen actually here? Current will be like, this will be forward bias, current will be going this way, still I will be high, and V minus IR, so Y output we will be getting still 0. So here in this situation, A 1, B 0. Then D1 you can write reverse bias, D2 it's forward bias, so I it's high, and then we will get Y output voltage will be still low, so Y will be 0, and so on. You can check for the next condition. When let's say both are connected to high, then what will happen? Actually both are reverse biased, D1 D2. So I am writing next operation, that is like A equal to 1 and B equal to 1, means both are high. So both are high means both are reverse biased. So you can write D1 and D2 both are reverse biased. Reverse bias, no current will be flowing this way. So then I will be what? 0. I is 0, then Y output will be equal to what? Battery voltage, and that will be like high. So here you can write Y will be 1, and this is what exactly AND operation. So this is symbol for AND gate. That is the main function. This is the realization using two diodes connected in reverse bias connected to the battery like this, and the Boolean expression for the AND gate is written this way, and we can read it like Y equals to A and B, and here the truth table. So truth table in case of A and B, here see A and, actually if I just go for mathematical understanding, that means it's multiplication actually. So like either of, in multiplication either of this is 0, then output will be 0 actually, right? So if 0 multiplied by 0, we will get 0, 0 into 1, still we are getting 0, 1 into 0, still we are getting 0, and 1 into 1, then only we will get 1. So when both are high, then you will be getting high. This is actually called AND gate, right? Let's see next one. Next, NOR gate. NOR gate, it's not exactly like new, basically it's combination of the two gate that we have studied. So it's basically OR plus NOT. OR means like this is OR gate, input A, B, and output, let me write it Y prime, then one connected NOT gate, and finally we are getting Y output. So here what is this? This is like Y prime, you can write it's A plus B, and then Y is what? Y is equal to Y like prime inverse or bar. So finally we are getting like Y is equal to A plus B bar. This is the Boolean expression for NOR gate. So its NOR gate is basically inverse of OR gate. Whatever the output you are getting in case of OR gate, just reverse that, inverse that, then it will be your NOR gate. So the truth table we can form it easily. This is A, B, and let me write it Y prime and then Y. So OR gate 0 1 1 1 0 1. Then in case of OR gate, what is the output here? 0 1 1 1, and it is the inverse Y prime, like Y is what? Y prime, inverse of Y, so we will get 1 0 0 0. So this is the basically output of XOR, or like sorry, NOR gate, means inverse of OR gates. So the symbol is this Boolean expression. This is your truth table. Similarly, we have one more combination that we call NA and D, NAND gate. So NAND gate means it's AND plus NOT gate. Then so AND gate, we know actually AND gate is this, and we have already understood now the function of AND gate, right? So this is AND gate. Now if NOT is connected across it, just next one is NOT gate is connected across it. So this is, let's say, Y prime, and this is the final output Y. Then what is Y prime? Y prime is equal to A and B, clear? And Y is equal to inverse of Y prime, and that is equal to A dot B, or A and B bar. So finally we are getting actually output in case of NAND gate, that is equal to A dot B bar. This is NAND gate. So again, what is happening here? AND gate, just inverse of that, so we can easily form truth table. This is Boolean expression. The truth table for NAND gate will looks like something this. For understanding purpose, I am writing the truth table for Y prime also. So this is A, B, 0 0 1 1 0 1 0 1, and then what we get? 0 0, then we get 0 0 0, and only in case both are high we are getting inverse. So this is Y prime, output of AND gate. Now when it is passing through NOT, it will just simply inverse, so it will be like 1 1 1 and 0. This is final output. And okay, first thing is like this is a combination that resulting forming NOR gate, but it is effectively just, this is OR gate. Just wait. And if I am using dot, then it form basically, this is NOR gate. A, B, and this is output Y. And here in case of similarly NAND gate, you will get and my one dot here. So this is symbol for NAND gate. This is Y, A, and this is B. So this is NAND gate, this is NOR gate, truth table, function, Boolean expression. These are the things you should keep in mind. They will be used for solving problems. So XOR gate, this is also called exclusive OR. Here we get output Y high only when either of input A and input B is high. We get high only when either of input A and B is high, but not both high. So that is called exclusive OR gate. Its Boolean expression Y is written as A dot B, A bar dot B plus A dot B bar. This is the Boolean expression. Its symbol, it's something related to OR gate. This is OR gate. Just add one more this, and this is XOR gate. This is A, B, and output here we are getting Y. The this can be even formed from AND and OR, not AND OR gate. So that is, let's say, A and not, and here another B not, and this. Now here AND gate, and here also AND gate. So this is what A, then this is A prime, this is B prime, this is B, and this is A, right? So what will be here? It will be like A bar dot B, or A bar and B, and this will be A and B bar, and then both are combined to or passes through OR gate. So actually, like, this is equivalent to this. This is your exclusive OR gate. So why, see, these two passes through an OR gate, then why we are getting basically A bar and B plus A and B bar. So this is your exclusive OR gate. And here, what is the function here that we have already I just told? So this is A input, B and outputs 0 0 1 1 0 1 0 0 1. Then when either of A and B is high, only then we should get high. So it's 0. When either one high, then we are getting high, and both are high, then also we are getting low. This is called XOR gate or exclusive OR gate. And similarly, we have another one, that is XNOR gate, means exclusive NOR gate. So here it's just inverse of exclusive OR gate. So this is OR gate, XOR gate, just inverse of this is called exclusive. This is A, B. So Y will be equal to what? This here it comes A dot B plus AB. This is your exclusive NOR gate or XNOR gate. And here, so remember, this is for XOR gate. The truth table for this will be just inverse of this truth table, and we will get, this is input and output Y A B 0 0 1 1 0 1 0 1. So here we were getting like when both are high, then we were getting like high, either one of high, then we were getting high. Here it will be like inverse of that, so it will be 1 0 0 and 1, and this is your XNOR gate. So these are different possible type of gates. Just remember their function, their truth table, and their boolean expression. That is like important. Next comes, actually sometime you will be given some combination of gates and you will be asked to get the final expression or maybe some truth table. There is something like that will help, and that is called Boolean algebra. So let me tell you some properties of Boolean algebra and how it exactly works. Then just go through them and learn them. It will help you in making your problem or solving problems easily, whatever they're coming on this topic. So let me next talk about Boolean algebra and its properties. Okay, here we have fundamental laws and theorem for Boolean algebra. Try to understand them and try to remember them. For remembering, you just write them 3-4 times. It will be like in your mind, you will be able to use them. Let's understand what exactly are these. These will help you a lot in solving like problem based on logical operations or logic gates. And so first let me explain you all the theorems here. And another thing is that here, because it's logical operation, it's not like simple addition or multiplication, like 1 plus 1, that means high plus high. So we can't get too high, it will be like simply high. Similarly, high plus low, then it will be like basically low, high plus low, we will get high. So it's like 0 plus 1, you can get 1. 1 plus 1, still you will get 1, not 2. Understanding, this is a 1 here, it's representing something logical. Actually, it's not a decimal number, it's not 1 plus 1 equal to 2. So that you should keep in mind. And then we will like here we have used x, y and z. So x, y are all like Boolean variables, so they can take either the value of 0 or 1. Then all these operations can be performed. Like these are sort of like representing the rules for Boolean algebra. And let's try to understand. So here x plus 0, so means x can be like, it can be 0 or 1, so you can understand easily, straightforward. If x is 0, then what will be this? X plus 0 means 0 plus 0 x, and what is that? 0. So 0 plus 0 we will get 0. Similarly 0 like x plus 1, then whatever, it can be either 0 or 1. So if it is 0, then we will get still 1. If it is 1, then 1 plus 1, still we will get 1, right? So similarly x plus x naught, this is x naught, inverse of x, so we call it complement of x also. Then x plus x naught, so let's say if value of x is 0, then what will be? This will be 0 plus x naught means 1. So 0 plus 1, you will get 1. If I am taking the value of x is high, means 1, so 1 plus, then it will be what? 0, then still I am getting 1. So that's how we are. Similarly x plus x, so this is like, either you are like x value is 0, then 0 plus 0, you will get x, that is 0. Or if value of x is high, means 1 plus 1, still we will get 1. So these all cumulatively are called OR operations. Similarly multiplication of Boolean, like multiplication in Boolean algebra, x and 0, then we will get 0. So these things you can straightforward understand. Actually you to verify them, just take the value of x either high or low and check, you will get exactly same thing. So that is basic simple operations. Like x double complement, so here what we are doing, x is something input, so one complement, then you made it x naught, and again if you are passing through naught, then what you will get? Exactly same thing, right? So x double complement, then we will get exactly same x. X plus y, whether you are adding like 0 plus 1 or 1 plus 0, it's same thing, and we call it simply commutative law. Similarly same thing for AND operation or multiplication basically. So here addition of 3, or basically associative law, x plus y plus z, so you add either x plus y then z, or y plus z then x, it's same thing actually, and you must be even getting it straightforward. Similarly another thing is, whenever you are feeling problem, something like not understanding, simply substitute, take the value of x, y, z, either 0, 1, 0, 1, 1, 0, or anything like high and low, take either value and check it on both sides by substituting, you will get exactly same thing. So that will prove it also actually. So 12 also you can understand straightforward, but remember, and like these are simple things actually, you can easily like it's not even difficult to remember also. So x and y and z, so here if y and z are like operation is performed first, then and operation with x, or x and y is performed first, then operation and operation same with z, still we will get same thing. So this is called associative law. This here x and y plus z, that will be by, you can simply like x and y plus x and z, so it's a distributive law. And here this is 15, something different. Let me show you the proof for 15. So 15, here we are getting like x plus y plus z, so x plus y z, this is x plus y and x plus z. So I will prove it by LHS, RHS. So this is LHS left hand side, and this is RHS. Right now it seems different. Let me just so if I operate it, then it will be like x plus y, and this is x plus z. So it will be like what? X into x, x and x plus x and z, and y and x plus y and z. This is what we will get. Now x and x will be equal to simply x, because 1 into 1 or 1 and 1, it will be like 0 and 0, it will be like 0, 1 and 1, it will be 1. So x and x is equal to x, then plus x and z plus y and z plus y y and x, and then yz. So now if I'm taking x common from here, then it will be x 1 plus z, and y and x plus y and z. So what is 1 plus z? By this property, 1 plus z, then it will be like what? 1. So similarly it will be 1, so it is x plus y and x plus y and z. Y and x, or it can be either x and y, it's same thing. Then I can take again x common from here, then it will be 1 plus y and z, and you can take, what is this? 1 again. So you're getting x plus y and z. So this you can see, this is RHS exactly equal to LHS. This prove actually this theorem 15 we call dual of distributive law. Next thing is x plus xz. So here it's simple thing. You can take simply x out, then it will be 1 plus z and we will get simply x. Similarly here x bracket x plus z, so just multiply it basically, open it, x dot x plus xz, is it? So then x dot x will be x plus xz, take x out, then 1 plus z, then you will get again x. So this is called law of absorption. So here z is basically getting absorbed. Next is x plus x bar or x naught y. So let me prove that too. See it. So next one is 18. So this is the proof for 18. It's x plus x naught y. Now here you treat it, this is x, this is y, this is z. Then this seems something matching with this. Then I can write it actually, this is x plus y and x plus z, and z is actually y here. And x plus x naught is equal to what? X plus x naught is equal to 1. So you will get this is equal to what? 1 dot x plus y, and what is that? That is x plus y exactly. This is x plus y. Similarly here also I can like 19 x and x naught plus y. So you can further like x dot x naught plus x y. Now if you here like x dot x naught, it's already there, x dot x naught always 0. So this is 0, then it is equal to simply xy, and that is what exactly a 19th theorem. This is De Morgan's theorem. These are very important actually, and I will prove those with the truth table actually. So let me show you the proof for theorem 19, 20 and 21. So 20, so by perfect, this is called perfect induction method. So here this is x, y, x naught, y naught, is it? Then what we need here? X plus y, x plus y, and we will need also x plus y naught and x naught dot y naught, all we will. So here it's 0 0 1 1 0 1 0 1, right? X bar just x naught inverse 1 1 0 0, and y it's 1 0 1 0. X plus y, this that is basically 0 1 1 1. X plus y in naught, so it's 1 0 0 0, and x naught dot y naught, x naught and y naught dot. So dot means like multiple, this is 1 and 0, and this is 0 and this is 0. So you can see this is what? X plus y naught, this is LHS, and this is what? RHS, and you can see we are getting exactly same. So this proof actually De Morgan's theorem, that is theorem 20, is it? This is called De Morgan's theorem. So this is also exactly equal. Similarly I can prove this x dot y also. So let me just erase part of it, and here we have, I'm erasing this part. Now so we already have like here this one also. Let me write here x naught y naught plus. So x naught y naught, adding this is 1 1 1 0, right? And x dot y, x and y, so x and y, then it will be 0, it will be 0 0 1, and x dot y naught, so just inverse 1 1 1 0. So here also you can see this is LHS and this is RHS. These two are also coming out to be exactly same. So this is all about like some theorem, fundamental laws, and theorem for Boolean algebra. I hope you understand the proof of every theorem, how they are actually like valid and right. Just try to remember them. Let me show you some example based on those, like how by using this theorem we can solve some problem, we can reduce some complex expressions and all that. So application of this. Okay, let's see some application of Boolean algebra. So here we are given two expressions, and it's asked to simplify the Boolean expression. So let's see how we can use the Boolean theorem and laws of fundamental law of Boolean algebra, and we can simplify these two expressions. So let me solve first one. It's x plus y naught x naught plus z. So for this I can first simplify this two part, x plus y and x plus y naught. So let first simplify only x plus y, then x plus y naught. So this is equal to x dot x dot y naught x y x and y naught. So here this should be 0, x dot x, that is equal to x, and this is x x dot y naught plus y dot x. Okay, because this y dot y naught will be equal to 0. Now we can simplify it. So from here I can take x, this is x, and from there I can take x out, then it's y plus y naught plus y. Y naught plus y is equal to 1. So this is x plus x, and that comes out to be finally x. So this part we are getting only x. Now multiplied by this, so next step is x plus y x plus y naught x naught plus z. So we got this is equivalent to what? X. So I can write it x, and this is x naught plus z. Then further multiplying x naught plus xz, and again what is this? X dot x naught or x and x naught, that is equal to 0. So we are getting finally xz. So this is our expression. So actually like this Boolean expression is simply equivalent to this one. I hope you understand how with the help of theorems and laws of Boolean algebra we are able to simplify this very easily. Similarly, let's see next one. So this is x y z x y naught z x y z naught. So again let's first go for this, and this implies x z, I'm taking out y plus y naught plus x y z naught. So this is y plus y naught is 1, then this is x z plus x y z naught, because this quantity will be simply equal to 1. Now what we can do here, actually in this I can take first x out, then it's x z plus y z naught, and here I can use dual of distributive law, dual of distributive law. So this is like I'm first simplifying it, writing it in different form, z plus z naught y, because x dot y is also equal to y dot x. So this can be, and then by using this I can write it x, and this is z plus z naught, and this is z plus y. And what is z plus z naught? That is equal to 1. So this quantity is equal to 1. Then we are left with here x multiplied by z plus y, and finally we are getting this xz plus xy. This is the final simplified form of this expression also. So this is application. In this actually, first thing is some little bit complex expressions are given, or either some logic gates will be given in different combinations. So instead of like simplifying them and you will be asked what is the final result. So what you can do there is that just write the Boolean expression, apply according to the logic gate, apply the operation and get the final expression, and then just by final expression you will be able to write comment what exactly it is. So that is the like way it will help you in solving and simplifying problems. Another thing here I just want to mention is that we studied, or normally we are given with all those logic gates with either one or two inputs. What will happen in case if, let's suppose, for OR operation or OR gates, three inputs are given, is it? So that's just a small point I want to mention. So when even like you are given with more than three or more than two number of inputs, still things are exactly same, it does not matter much. So for AND gate, OR gate, something like that. So see, OR gate with three input. In this case, what will happen actually? This is your OR gate and inputs are three here. Let me change the marker. So here we are having input A, B and C, and we are getting Y output. So again by Boolean algebra it will be simply A plus B plus C, and now whatever the possible combinations are given for this, you should be able to answer it what will be the final output. If you want the truth table, you can get it truth table also. So here this will be like truth table A, B, C and output Y, is it? Another thing is here we have three input variables. So how many possible combination logics will be there? That can be given by 2 raised to power n, that is 2 raised to power 3, that is equal to 8. So here it will be like 0, 0, 0, 0, 1, 1, 1, 1, then 0, 0, 1, 1, 0, 0, 1, 1, and then 0, 1, 0, 1, 0, 1, 0, 1. Now if all lows are added, is it, in or passing through OR, what we will get? 0. Either one of them is high, we will get still high. So here also we are getting high, high, 1 high, still high, 2 high, we are getting high, high, and this is high. So this is simple like OR gate with even 3 inputs. Similarly, exactly you can go for even like AND gate, XOR gate, NOR gate, NAND gate, even anything for more than 2 inputs. So I hope this is all about your logic gates and Boolean expression and binary and decimal system. And here we finished semiconductor and semiconductor devices. Just go through like more problems from either book. We will give you assignment, just solve it. I hope you will be in position to answer all the problem based on this topic. Thank you so much. Let's see you with the next topic in the next class.